Okay, in section 2.2, we were looking at limits and talking about them in numerical and graphical way. We're going to now get into the analytical view of it. Again, just to remind you that we are looking at f of x. When we say f of x, remember, we're talking about the output values of a function. When we talk about the output values becoming arbitrarily close to a single number L, again, L is the same thing. It is also an output value. So our outputs are coming very, very close to a single value. We're looking, remember, that we want to know as the input approaches, and I see I have something missing here, as the input values approach some destination that we have decided, or we're told is decided, we want to know what's happening to the output values. Now, one thing that we haven't talked about is, although we alluded to it briefly in our lecture last Thursday, is that the limit does not depend on the value of the function at x equaling c. Remember, we had a couple of those problems where we were looking at, and I'll just make one up here, we ended up with maybe something like this. As the inputs are approaching this value c, remember when we do a limit, we're talking about from both directions, even though this value is not, this point is not included on the graph, we still have a limit to the outputs as the inputs approach this value c. Now we're going to talk in this section about what we call well-behaved functions. And we all like well-behaved people, and we have a definition for functions as well. By well-behaved, it means we can use direct substitution. Now what that means for us is we're going to take our problems that are given to us, and we're going to do the best we can with as much algebra and mathematics that we have learned from other math courses to get them to be well behaved, so that when we are trying to find the limit, all we have to do is to make a direct substitution of that input value that we're approaching. We can just directly substitute that into the function that we're evaluating. We find out that well-behaved functions are continuous at the point that we are discussing. So we're not going to have any situation where, as we did before, where we could not use that value c in our function. And this is going to help us out too. All polynomial functions are well-behaved functions. So if we have a polynomial function, we're going to know that that is one that we can use direct substitution on. Direct substitution is our friend. We really want that to happen. Okay. Now, we have then some basic limits, and these are, again, very basic. They're not sophisticated functions at all. If we have, and we're just going to take a look at the functions here, b, another function x, and another function x to the n. So if we're looking at, let's say, f of x is equal to some value b. Now b is not going to be a variable, it is a constant. What type of a graph do we have for that? Again, remember, we're talking this value b is a constant, and so if you're saying to yourself or to whoever you're working with, it's a constant function, therefore, if this is the value b, we're going to have then a graph that's a horizontal line. You're absolutely correct. Now, if thinking about that, if I have c down here as the value I'm trying to approach on my input values, as I let x approach this value c, what's happening to my outputs? If they're all going to be the constant, then therefore the limit of the outputs is that constant value. Okay, we go down to the next one here. We would have, in this case, f of x is equal to x. And if you think of this as an Algebra 1 problem, I think every single one of you know exactly what that graph looks like. Something along that nature. And here again, if this is my value c, and I'm letting x approach c from both directions, what are my output values approaching? Keep in mind that we're always considering what's happening to the outputs, the output values. And so the output values are approaching this point over here, and if these are the output values, then this would be f of c, and since f of c is in the function f of x equals x, then that's just the value c. So if we have just our simple linear function, we would have the limit as our inputs approach the predetermined value, the output values are approaching then the same value. Okay, now if you take a look at this one, the third example down here, our third example is going to be f of x is equal to x to the n power, and n is going to be up here at the top. It says n is any positive integer. So we could have f of x equals n could be 1, and so it could be f of x equals x. If n is 2, we'd have f of x equals x squared, so forth and so on. Now the one question I want to ask you is, x to the n, for n being any positive real number, is that a polynomial function? And we would say, as long as it's a positive integer. Now let's go back up here and highlight that. It says let n be a positive integer. So that takes away the possibility of to the 1/2 power, which would be then a square root. So we are going to be staying with examples, f of x equals x squared, or f of x equals x cubed, etc. So these are polynomial functions. And what did we just say on the other slide about polynomial functions? Take a moment if you need to. Go back and look at that. We said that all polynomial functions are well behaved. If they're well behaved, we like that, remember. If they're well behaved, it means that they're continuous at that value, but more importantly, it means that we can use a direct substitution. So the fact that this is x raised to a positive integer, we can use direct substitution. And so, if we had the parabola, for instance, and this is the value c, then as we approach c from both directions, our outputs are approaching an equivalent value, which would be f of c, which would be c squared, whatever c happens to be. Okay, so these are the basic ones. And if we can reduce our complicated functions down to one of these, then we can know that our value, or the limit of our outputs, are equal to what we see here. So keep that in mind. Okay, let's go on to our next page. We're going to open up a calculator page. So let's go to our Inspires right now. And remember, we're always going to take a new document, and if need be, if it says, do you want to save, unless it's something you truly want to save in a folder, you just say no. So let's open up a calculator page, and let's look at exactly what this can be in a calculator page here. Some examples here. So let's look at the limit, and I'll write these out as we go along. We're going to look at the limit as our inputs approach 5 of the value b. Now I'm going to assign b to be some various values here. And so in the first iteration, let's let b equal 2. And so we're going to go over here and let's put that limit in. Now there's a couple ways to get to our limit. We can either go to Menu and go to Calculus and go to Limit. The other way that we could do that is to go into our templates. And so if we look at, let me erase that for a moment. There we go, this button right here, go into the templates and we have our limit in this location. Let me show that to you on the gray model here. Menu, same way, Calculus and Limit. And if we go into the template, it's Control on the multiplication sign, and that's where we find the templates for this. Okay. So let's see, we said we wanted this to be X and tab, and we want to approach 5 and tab. Now remember, this location is reserved for our approaching it from one direction, like from less than 5 or from greater than 5. We're just going to have an approach from both, so we're not going to work with that. And tab, and let's put the value of 2 there, and we're going to press enter, and just as we saw on the other page, it is in fact 2. If we repeat that, and we'll go in here and do another limit, and we have X approaching, and tab over here, approaching 5. And let's now use the output of, the function, the constant function of -3. Before you press enter, let's kind of take a guess. What do you think it's going to be? And you're right, it is going to be -3. Okay, I'm going to